So maybe we should. Number one, okay, did you want to look at number one, either of you?
Yeah.
You got it or no?
Oh, yeah.
Okay. So if you have one A, look at, sine squared times cosecant squared minus one. If you're stuck and you don't know what to do, which might happen, there's a trick here. You can use that tangent squared plus one equals cosecant squared to replace this if you want, using that identity. This would be, well, this would be made easier by that, but if you don't recognize what to do, then you replace cosecant squared with 1/sine squared so that everything is in terms of sine and cosine. So I'll use that rule to put or the rule of thumb to put everything in terms of sine and cosine. And now I say, well, wait a minute, if I multiply this times this, I just get one. And this times this is minus sine squared, right? Just multiply out. So put it in terms of sine and cosine only when you're stuck. And then multiply out just like you would in algebra to see if it simplifies. Oh, wait a minute, one minus sine squared is cosine squared by the Pythagorean identity. So you can recognize that here, this comes out to be tangent squared and sine squared times tangent. This also. Either way, this is as simple as you can get it, this cosine squared. This one, because sine squared plus cosine squared equals one, remember this is the one, cosine squared is one minus sine squared. All right, one B says suppose you have sine squared theta over one minus cosine squared theta. Again, recognize one minus cosine squared is sine squared. This is sine squared over sine squared. All right, and so it's one. But it depends crucially on that identity that sine squared of any angle plus cosine squared of the same angle is equal to one. That's what tells you this last step here. Very important identity, the Pythagorean identity. All right, then number two, then we had a terrible problem with number two. I think that was just a lot of people going the wrong direction. Was good at that one, so I want to make sure I do this one. Cosine 2 theta equals 1/3. If you see a multiple angle, what you want to do is substitute u equal that angle. So let's let u equal 2 theta. Get cosine u equals 1/3. Once you have a trig function equal a number, you can solve it on the unit circle for that angle u, right? So cosine u is x, and I'll solve the unit circle with x equals 1/3 about here. And observe that there's exactly two angles, this one and this one, that have x equal 1/3. So you say, well, what is this angle here? I know one angle that satisfies cosine u equals 1/3. It's u equals arc cosine of 1. Now by symmetry, if that's arc cosine of 1/3, then so is this one. And now I see two angles, but then 0 to 2 pi that have cosine equal 1/3. It's arc cosine and 2 pi back up arc cosine. So now I observe that all angles u that will make the cosine of u equal to 1/3 from that diagram must be arc cosine 1/3 or 2 pi back up arc cosine of 1/3. And then all coterminal angles apply, right? So you can put plus 2k pi, right? K rotations. So here's all coterminal angles, all angles that give cosine equal u equal 1/3. That makes sense how we got that? Cosine 2 theta equals a third, just change it to cosine u equal a third. Solve for all angles u on the unit circle, but angles that have x equal one, that lead to x equal 1/3, which is arc cosine, and 2 pi back up arc cosine. Now u is equal to 2 theta. We get all angles theta by dividing by 2. I get theta equals 1/2 arc cosine of a third plus k pi by dividing the whole x side by 2, or theta equals this divided by 2 pi minus a half arc cosine of a third plus k pi. Well, now you realize k plus pi plus an arbitrary multiple of pi is just an arbitrary multiple of pi, so you could just call this minus a half arc cosine of a third plus any multiple pi. You can call it k pi, or you can call it n pi, where n is k minus 1. So any multiple of pi is the idea. I just gave it a different letter so it wouldn't affect the same multiple. All right, and then which of those are between 0 and 2 pi? This is a hard problem, I think. 0 and 2 pi. You just have to take k equals 0 and 1 in each of these things. So if you take theta equals 0 here, you get 1/2 arc cosine 1/3. If you put k equals 1, you get 1/2 arc cosine of a third plus pi. Angles between 0 and 2 pi. Put 2 pi, then 2 pi plus a positive number is too big. And put k equals 0 in here. Well, let's say in here, we can leave this off. Let's say, put k equals 0 in here, and you've got pi minus arc 1/2 arc cosine of a third. Put k equals 1 in here, and let's see, you've got 3 pi, I'm sorry, 2 pi minus that. And finally, the problem says round it to 2 decimal places, and that came out to, oh, I have it somewhere here. Yeah. It's approximately 0.62 or you can add pi to that, pi plus 0.62. Cosine. 3.76. Let's see. Looks like 5.67, I think, on that one. Anyway, you just have to put the decimals to these. The 2 pi minus this was 5.67. 2.53. So there's 4 different answers for that one, if you calculated these things to decimal places. That's probably the hardest task. Then I wanted you to do some non-special angles that can be done exactly. For instance, 3A, if you wanted the cosine of minus 105 degrees, there's actually 2 ways to do it. You could do that with the half angle formula, or you could do it with the sum of special angle. I would first do this, say cosine of a negative angle, since cosine is even, it's same as the cosine of a positive angle. Get rid of all those minuses I would have. I just need cosine of 105 degrees. Well, 105 degrees can be written as the sum of special angles as 45 plus 60. That's the easiest way, the smallest angles you can add it. And then remember cosine of the sum is cosine minus sine. With the angles in the same order, 45 degrees, 60 degrees, 45 degrees, 60 degrees. Then you have to be able to take your trig functions to special angles, right? You need special triangles or the unit circle. Pi over 4 of 45 degrees. And then 60 degrees. Square root 3 over 2 is 1.5. So this one would be cosine would be a half. This would be square root 2 over 2. This would be square root 2 over 2. 3 over 2. If you simplify that, then that just comes out to be square root 2 minus square root 6 all over 4. That was the answer to 3A. Okay. Just write it as a sum of special angles and then use the sum of angles formula. Okay, let's try 3B. 3B looks like this. Suppose I want the cosecant of 11 pi over 12. Again, you use sum of special angles, or you can use the half angle formula. Each one works. If I use the sum of special angles, I could call this cosecant of 7 pi over 12 is what I use here. I think of 4 pi over 12. Oh, I use 9 and 2. I'm sorry. 9 pi over 12 and 2 pi over 12. There's different ways to break this up. And then I don't have a sum of angles formula for cosecant, so I rewrite it as 1 over sine of the sum of special angles. And then I'll rewrite those in the way we're used to. 9 pi over 12 is 3/4 pi. 2 pi over 12 is 1/6 pi. Then I use the sum of angles formula for sine, right? Sine, cosine plus cosine sine. So sine 3 pi over 4, cosine pi over 6, plus cosine 3 pi over 4, sine pi over 6. And then you put in what these are. Sine 3 pi over 4 comes out to be square root 2 over 2. Cosine pi over 6 is square root 3 over 2. This one is square root 2 over 2 minus circle. And sine pi over 6 is a half. So you get that. And then algebra. With algebra, this is actually reduced to square root 6 plus square root 2. Why don't we do the algebra? I think I'd rather skip it. But there's the exact angle, and then algebra reduces it to that. Okay. Feel comfortable with this when you see it again? Is it clear or is it good? Okay. That's the idea. If you got one of these angles that's a multiple of 15 degrees, that's a multiple of pi over 12. Use the sum of angles theorem to rewrite it, right? On both of those. Here's number 4 to establish an identity. I think these are kind of hard. They're always intimidating, these proofs. Show that cosine of 4 theta equal to 1 minus 2 sine squared 2 theta. Well, what I can do is say cosine 4 theta. I don't have the same angles in here, so I'm going to have to use that something that changes the angles. That's twice the cosine of 2 theta. And then I use the double angle theorem. So I say cosine of 2a is cosine squared a minus sine squared a. 2 theta. Now they're all in terms of 2 theta. Oh, wait a minute, I see what to do. Cosine squared is 1 minus sine squared. This one. And then 1 minus 2 sine squared is that one. So that was the proof of that one. It's just sort of to recognize that this is the double angle identity with 4 theta, 2 theta replaced by 4 theta, or theta replaced by 2 theta, I guess I should say. So if you just said that, this is the double angle, one of the double angle identities with theta replaced by 2 theta. I write the expression as a single trig function. The object was to recognize it looks like an identity. It had sine 2x sine x plus cosine 2x cosine x. Well, this is a little easier if you rewrite it in the other order. If you say sine plus cosine cosine, that sounds kind of familiar, but I think it was cosine plus sine sine. So let's rewrite it in the other order. Cosine 2x cosine x plus sine 2x sine x. I'll change the order of addition. And now it's cosine A cosine B plus sine A sine B. Oh, that's cosine plus sine. Sine is cosine of A minus B. Right? That was the identity. Where A is 2x and B is x. Oh, this is just cosine x. So that was all a fancy expression for cosine x. Let's see, number 6, the double angle identities find the indicated value. Yes, okay. Number 6. If cosecant x minus square root of 5 over 2 and cosine x is less than 0, find sine 2x. These problems where you're given a trig function, has to find a trig function of a double angle. The first thing you do is write down the double angle identity. Sine of 2x is 2 sine x cosine x. Some people just pulled the 2 out. I said you would. And wrote this. That's not true. You can't just pull the 2 out. This is the identity, 2 sine x cosine x. All right, and now, so I just need to know what sine x and cosine x. But from cosecant, I know immediately that it's reciprocal. Cosecant x equals square root of 5 over minus square root of 5 over 2. Says that sine is its reciprocal. Sine x is minus 2 over square root of 5. And then if you know sine, you know cosine, right? Because it's plus or minus the square root of the sine. We say cosine is less than 0, so take the minus sign. Let's minus square root 1 minus a minus 2 over square root 5 squared. Well, that's 1 minus 4/5. 1/5. And then you reduce it to minus 1 over square root 5. There it is. So this is 2 sine. Sine was minus 2 over square root 5. Cosine. Cosine was minus 1 over square root 5. Oh, it's plus 4/5. That was solving that one. Number 6 was a short one. Or 7, excuse me. 7 was a short one. If you have y equals 6 cosine pi x over 4, you're asked to find the angular frequency. This. Frequency. Well, this is A and this is B. So the angular frequency is just B. So it's, we read it at pi over 4. The period. T, as we recall, is 2 pi over B. It's just memorizing. It's 2 pi over 4. You work out the quotients, that's 8 exactly. And then the frequency is the reciprocal of the period, but 1 over P is 1/8. So those are the 3 answers there. Pi over 4 is the angular frequency. How many radians per second are going by? Period, it takes 8 seconds per complete one cycle, and then frequency is 1/8 of a second. Cycle we go by. All right. Number 8 was also kind of a short one if you recognize it. The trick was to recognize square root 1 plus cosine pi over 3 over 2 simplified by a half angle identity. So you have to know the half angle identity, this one. Well, it looks like a half angle identity, right? The half angle identity says plus or minus the square root 1 plus cosine 2 theta, 1 plus cosine theta over 2 is equal to cosine of a half theta. All I have to do is say if this is theta, then this whole thing must be plus or minus. We can switch the plus or minus to the other side, right? They're equal to plus or minus each other. This is plus or minus cosine of 1/2 theta. Theta equals pi over 3. Right? So it's just plus or minus cosine of pi over 6. That's all I wanted, was just to simplify it. And then it's a plus or minus. Well, this one, square root means a non-negative number that has that square. Pi over cosine pi over 6 is positive, so we have to choose positive. So we have to choose the positive sign to make positive the next positive there. So cosine pi over 6 is the answer in that one. I said don't evaluate, so just leave it like that. Plus uses this. Nine says solve these exactly. So these are going to come out to be special angles, unlike the other one that has ugly decimals, right? The first one is square root 3 cosecant theta minus 2 equals 0. What you want is trig function equal to number, so you add 2 and divide by square root 3, and you get cosecant theta equals 2 over square root 3. Then, if cosecant, to solve this on the unit circle, we really don't want cosecant or secant. We take the reciprocals and say, that's the same as sine equals square root 3 over 2. Reciprocals. And now sine is the y coordinate. I can solve that in the unit circle. I'll go up to find all points in the unit circle where y equals square root of 3/2, close to 1, something. And I observe that there's exactly two terminal rays. And I wonder what they are. Well, you drop the perpendicular and make a right triangle to find out, right? And if this goes up to y equals square root of 3/2, this side must be square root of 3/2. This is 1 because it's a unit circle. This must be a half, and this must be a pi/3 angle. So one solution to that is theta equals pi/3. But there's another, right? By symmetry, this must be pi/3. This angle going over here then must be pi back up pi/3. Pi minus a third pi must be 2/3 pi. So that was it, just those two. Being solved for exactly by rewriting cosecant equals 2/√3 as sine theta equals square root of 3/2 and solving it in a unit circle. Always looks easier afterwards, doesn't it? All right. Now, 9b, this is one of the harder ones. If I have 2 cosine squared theta minus square root 2 cosine theta equals 0, I've got a quadratic equation in cosine theta, right? I've got a cosine and a cosine squared. So the trick we learned there was we could let u equal cosine. Rewrite this as a quadratic equation. 2u squared minus square root 2u equals 0. Because this notation means cosine theta squared. That's what the notation means. So this is u squared. All right, now I can do it by factoring or the quadratic formula. I can factor a u out, call it u times 2u minus square root 2 equals 0. By factoring. And that says equivalently that one of these factors is 0, either u equals 0 or u minus square root 2 equals 0. Equivalently u equals 0, or this one, if you add square root 2 and divide by 2, you get u equals square root 2/2. So now I have 2 unit circle diagrams, one for each case. This original equation is completely equivalent to these two, right? And then I can solve each of the unit circle. The first case, I have u equals 0. Let's rewrite this. U was cosine theta. This is cosine theta equals 0, or cosine theta equals square root 2/2. I should give you a copy of the key here after we're done here, shouldn't I? Xerox it. That's not the answer. But it'd be easy to Xerox here right afterwards. All right, if you want. Or I'll probably put it up in D2L shortly too. Cosine theta equals 0 is x equals 0 in the unit circle. It's this line, x equals 0. Cosine theta equals square root 2/2. It's this line, x equals square root 2. So there's 2 terminal rays here and 2 terminal rays here. Well, what are the angles? Pi/2, evidently. Or all the way around here, pi/2, pi, 3 pi/2. Then 2 of them over here. This looks just at a 45-degree angle. If x equals square root 2/2 on this side, and this is 1, it's 45, 45, 90 triangle. That's pi/4. Oh, this is pi/4 by symmetry, and you get pi/4 and 2 pi back up pi/4. 7 pi/4. Those are the 4 angles for that. Okay. So 4 angles on that one. Then the last one with this memorizing identities. You want to put in the letters on there. So another expression for something equals sine squared x was I 1 minus cosine squared x. I think most of you got most of these right. If you want another expression for cotangent x, it'd be b was cosine x over sine x. So that's checking your quotient identity. Another expression for secant x was j 1 over cosine x. Put the letters in j, b, I. And then another expression for cosecant x was h 1 over sine x. And another expression for cosecant of minus x was d minus cosecant of x. Another expression for cosecant squared was L 1 plus cotangent squared. That was a harder one to remember, probably. One of the less used Pythagorean identity. All right, there it is. All the problems we managed to get through. Any other comments on the questions? Okay, so this next chapter is a little easier, and not easy, but easier than this one that we just did. And I think the material after this is even slightly easier than that. We were doing some of these law of sines problems, so I just wanted to do some more law of sines, particularly some applied example. It's amazing how many of these things come up in real life. Here's one up here. To find the distance across a river, this is number 10 on your homework here. We can do the following. It's found that angle B is 95 degrees and angle C equals 21 degrees if you're measuring from two spots where you can stand on the bank maybe. Then you can, you want to find the distance from A to B. So you can click on the picture to see it more clearly. Here's A, B, and C. It's probably hard to see back there across the river. And given that angle B, this one in here is 95 degrees, angle C over here is 21 degrees. We want to find AB. And BC is 300 meters or something. So use this diagram. Oh, it's hard to see. B, C, and A. We can blow it up there, but let's just do it here. B, C, A. And the river's flowing down here. And suppose BC equals 300. B is 95 degrees. C is 21 degrees. I think it really helps to draw it in. Put in 21 degrees, put in 95 degrees, and put in 300. And ask yourself, what case is that in triangles with sides and angles? Rotate either direction and get angle, side, angle. Oh, it's angle, side, angle. Then we go to the law of sines, right? Anything but side, 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 or side, angle, side is law of sines. So we'll say we can do this quickly with the law of sines. we can say this, we always want to use a side and an angle opposite in order to get three of the four things known in the law of sines, but we don't have a side and an opposite angle, so I better figure A. A is 180 degrees less the two angles that we have, 95 degrees and 21. So the sum of the three angles adds up to 180 degrees. Let's see, this is 116, taken away from 180 is 64. So A is 64 degrees. Now I have an angle and an opposite side. I can put this in as I go if you want. Let's leave that there. That's the initial information. So now I know that sine of 64 degrees is to its opposite side 300, as what we're trying to find is AB, I think you're right. Find AB. So here, given these, find AB. So let's see. Is as the opposite angle to AB, which is 21 degrees. Is the distance from A to B. I don't want to write that. Right, distance from A. Or they just said AB. Let's just write AB. Follow that. Okay. Now you can use reciprocals, or you can use cross multiplication or some other method. And we'll say using reciprocals, this says 300 is to sine 64 as AB to sine 21. Multiply by sine 21 and you get 300 sine 21 is to sine 64, or divide by sine 64 is the length of AB, and we just run that on the calculator. I'm going to this in degrees mode, I think. All right, so 300 times comes out to be 119.6. Let's say 120 feet to the nearest foot. All right. That was the law of sines. It said sine of any angle is to its opposite side as the sine of any other angle is to its opposite side. And so it was three laws. We wrote it like this. Use their notation. Sine of angle A is the opposite side A, and sine B, and sine C is to C in any triangle whatsoever, where A goes opposite A, B goes opposite B, and C goes opposite C. In any triangle that holds, there's the law of sines. All right, so this one, I think is causing some trouble, so I want to make sure I looked at this one. This one says, you really, really need to draw a picture on some of these. The picture helps you figure out things because they don't give you enough information. The flagpole at a right angle to horizontal is located on a slope that makes an angle of 12 degrees with the horizontal. The pole's shadow is 16 meters long and points directly down the slope. The angle of elevation from the tip of the shadow to the sun is 20 degrees. The height of the pole is how many meters? It's hard even to follow the problem. It's so complicated, isn't it? As says, hint, draw a triangle and apply the law of sines. Note the shadow points down the slope starting from the bottom of the flagpole. Angle of elevation is the angle made with the horizontal, not with the ground, right? So this is what we're given here. Part of it is just learning these terms for angle, for angle of depression and angle of elevation. So flagpole at a right angle of horizontal. You have the ground makes an angle of 12 degrees with the horizontal. So here's horizontal, and here's 12 degrees, and this is the ground. And then the pole is at a right angle to the horizontal, so it sticks up at 90 degrees to the horizontal like that. And it's 16 meters long. I'm sorry, the pole shadow is 16 meters long. And points directly down the slope. So it's got a shadow that comes down here like this, coming from the sun. And this is 16 on this side. 16. The angle of elevation from the tip of the shadow to the sun is 20 degrees. The angle of elevation is not from the ground, it's the angle from horizontal. So this is 20 degrees here. What's the height of the pole? So what you do on these things is you draw a picture. Otherwise, we'd never figure this out probably. And then in this, you want to list all givens. Well, we did. And you want to list the desired quantity, H. Now we can try and figure this out. Yeah, dude. Here's what you do on these applied problems. You think, I want to get three things within a triangle, like side angle or angle side angle or something like that. I have a side and I can figure an angle out of this thing. Here's what you can do for one thing. You draw this thing over here and say, well, if this is 20 degrees, these alternate angles are congruent. This must be 20 degrees too, right? Two intersecting lines that have the same angle on each side. Once I know this is 20 degrees and this is the vertical, then these two, this is a right angle here because the pole is vertical. That leaves this is 90 minus 20, it must be 70 degrees. Now I've got it. I've got a side, let's see, and an angle here. Oh, I need one more. So actually, I've only got two, don't I? I say again, if this is, now I can look at these angles over here. This is 12 degrees here. That was given. If this is 12 degrees and it's a right triangle, then these two are complementary. So this must be 78 degrees, right? 78, 12 makes 90, and then the three have 180. That's 78, and then these two are complementary. So what you have to do is use the picture to figure three things in the triangle that you know, right? So if this is 78 degrees right here, and these two add up to 180, this must be 108 degrees. So that's how you have to figure this problem for the homework, right? Draw the picture, write the given numbers and desired quantities, H. Now, in the second part, you figure any obvious results. That's what I just did there. Obvious consequences. To get a triangle with three known quantities. Right? Because remember, if we have three other than angle, we can solve it by the law of sines and the law of cosines. Well, say three measures between the angles and the sides, not all just the angles. And that's what we did finally. I said, now I have a side, I have an angle, and I have an angle. Side angle, that's not familiar. Wait a minute, angle, side if I go the other way. So use the law for those measures. So the third step is I notice this angle, angle, side. For that one, I use the law of sines. Not side, 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 or side, angle, side. I'll just go to law of sines. So let's see, what I want in this thing is to find H. And let's see, I have an angle on the opposite side, so I can use those to get 3 of the 4 quantities known. That's what I need. I'll say sine of 70 is its opposite side 16, using the law of sines here, as I want to get H, so I need this angle. But to get this angle, I don't have it yet. I'm gonna have to figure it, right? So I'm gonna say now, if I call this angle, I need another angle here. So they call it alpha. Alpha in that picture is equal to 180 minus this one minus this one. So it's 180 minus 108.
Shouldn't that be 102?
Yeah, it's thinking that was too big. Yeah, this should be 102, so it adds up. Thank you. Yeah, minus 102 minus 70 gives me 8 degrees there. All right, so alpha is 8 degrees. So now I have sine of 8 degrees is to its opposite angle, alpha, is to its opposite side H. There we go. So alpha, this one over here is 8 degrees. Now I try and find this side, knowing this angle, and this angle, and this side, yeah, so. There we go. Now I've finally written the law of sines with 3 knowns and 1 unknown. I just solve for this. Once you do enough of these, you can kind of do it in your head, but let's do it slowly here. Right, reciprocals, 16 is to sine 70. It would have behooved us to write this in the reciprocals in the first place. You can, we said, draw the law of sines upside down. It works just as well that way. So here's where we could have started if we were smarter, right? All right, now multiply both sides by sine 8 degrees, and you get 16 sine 8 over sine 70 on the left equals H on the right. I just have to compute that. Oops. Get there. 16 times sine 8 by sine 70. This is 2.36 meters. Like, how many did it say? Doesn't say how many decimals to put in, but I get H equals about 2.36966787. So a little over 2 meters tall, 2.37 meters. If I click on this thing, maybe it'll show me some more. Yeah, this will be, it's 2.37. So that's the harder problem. I want to make sure I did at least one of those. Then I'm going to do one more ambiguous case, because that's kind of the hardest one in the section. Suppose I gave you this triangle here, for instance. And I said, suppose this angle here is 70 degrees. And this is Suppose that, side A, B is 20 meters. Side A is 16 meters. And angle A, or angle alpha, say A to follow their convention, is 40 degrees. Solve the triangle. I'll draw the picture. If you draw this, a lot of times you can get an idea whether, remember that this is going to be the side angle problem here. If I draw B is 20 meters here, and I draw A is 16 meters here, a little shorter, and I draw angle A here is 40 degrees, opposite it. So opposite side A is angle A. That could be the triangle like that, but if you think about it for a second, this side length is undetermined. It can go any length. I could also put the 16 over here like that, and make a triangle that looks like. So I can have this little white triangle, or I can have this red one. And they both satisfy the criteria. Once you sketch this, you can kind of see whether it's going to be one triangle or zero or two in general. If it's real close, maybe you have to actually do the calculation. But I'm going to say we'll expect two triangles there that actually have these measures. But side angle is not a congruence there, and there's actually can be 0 or 2 solutions or 1. We'll have to figure them out. All right, so longer than expected. So the last one now, what I do now is say sine A 40 degrees is to side A 16 as sine beta or B is to 20 meters. It's the equation I get by the law of sines. And it's set up so I only don't know one measure, that's the angle B. So I'll multiply by 20 and say, oh, that means that 20 sine 40 degrees over 16 is equal to sine of B. And now this is going to break up into two cases. What we said last time was when you have sine B equal a number, let's say D. All right. You can think of the unit circle and sine B equals a number D, which is always positive for the law of sines because the sine of an angle in a triangle is always positive. An angle between 0 and 180 degrees. The side lengths are always positive. You always get a positive number here. So here's y equals D. You treat sine B as the y coordinate. And you observe there are two angles here, recall. And so always in this law of sines side angle case, you get one solution is the arc sine of B, but the other one is 180 minus the arc sine of B, right? Because this is the arc sine of B also by symmetry. So the two angles you want standard position are the one at this terminal ray, arc sine of D, and the one at this terminal ray, pi minus 180, or doing degrees, minus arc sine of B. There it is. So that's what we're going to do for the two angles. But once we get sine B equals a number, we're going to break it up into two cases, 1, 2. And the first one, B is going to be the arc sine of the number you see there. It's 20 sine 40 degrees over 16. Right? Okay. And the other one is going to be 180 minus that. That's what we said here. One angle is the arc sine, one angle is 180 minus the arc sine. So it'll be 180 minus the same. I just have to figure out what this is. So I run this on the calculator. So this is inverse sine. Shoot, let's see. Oh, I did sinus the inverse sine. All right, 53.5 degrees. To one decimal place. So it'd be, and the other one has to be 180 minus 53.5 degrees. 126.5. All right, so two different triangles. This one has angle B equals this. That one has one angle B equals 180 minus this number. Once you have that, you can solve the rest of the triangle, right? Because I have A and B, I can now find angle C is 180 minus these two. 180 minus 53.5 degrees minus 40 degrees. Well, that's 93.5, so this leaves 86.5 degrees. This one, on the other hand, A will be 180 minus these two angles, 126.5 degrees and 40 degrees. I'll remind you what happens here too. If there's only one triangle, what you'll find out is you get a negative angle at the end here. If you get a negative angle, that means there was only one triangle. It's impossible to do this one. So you just keep the first one. But this one's not going to be negative, right? This is 13.5 degrees is left. So if you get two positive angles, then you know there's actually two triangles. So now I have all the angles. I just need to find the last side, which is side C. We'll say sine C, or let's write it upside down. Side C that I need is to sine 86.5 degrees, its opposite angle. As let's go back to the original numbers. Sine 16 meters is the sine 40 degrees. A is the side A. Now, if I multiply that by sine 86.5, I got C equals 16 sine 86.5 over sine 40. And I can run that on my calculator. Let's see, 16 times sine 6.5 divided by sine 40 is this 24.8. Now I've got the triangle solved. I've given three measures. Here's the other three. 53.5 degrees, 24.8 degrees, oops, not 8 degrees, 24.8 length, and 86.5 degrees. Then I have to finish this one also, right? Once again, I'll say C is the sine of the C that I'll get, well, this is C here, sorry. C is the sine of 13.5 degrees this time. As 16 is the sine 40. So solve for little side C from this angle C, and I get that C equals, just by multiplying by sine 13.5, 16 sine 13.5 over sine 40. All right, and let's see. That to be 5.0. I'm sorry, 5.8. All right, so I got the three measures for this one. So in this case, there's two different triangles. One of them has those three last measures and one of them has these three last measures. We did one of those last time, but one more, I think. But one of those is this triangle and the other one is this triangle. That's the law of sines. The law of cosines, I think, is actually a little easier, although it's a little harder formula to remember. Let's get started on that tonight. I guess we'll finish it next time. All right, this is the law of sines. It's the law of cosines. It's a theorem. And this will complete our ability to solve any triangle quickly given three measures other than angle, angle, angle. It says this, just like law of sines, it starts off in any triangle. Now you can apply it to right triangles, but nobody does because right triangle trigonometry that we learned is faster, right? But it does work. And the relationship to this between the Pythagorean and the Pythagorean theorem is actually striking here. In any triangle with the same convention as before, suppose I put angle A, opposite side A, angle B, opposite side B, and angle C, opposite side C. Or you can use alpha, beta, gamma. I like better. It's in more books that way. We have this, that C squared equals A squared plus B squared minus 2AB cosine, law of cosines, C. So this is a longer one, harder to remember in some sense. And then what's so special about putting the little side C? You can label these any way you want, right? So once you know this one, you can just relabel it and get the other two laws of cosines. This one has three laws also. You can also put A squared equals B squared plus C squared just by relabeling the sides and angles. Just so A is opposite A, alpha, A is opposite A, B is opposite B, and C is opposite C. So B squared plus C squared minus 2BC cosine A. Or you can put B squared equals A squared plus C squared minus 2AC cosine B. So there's three laws, three ways to rewrite the law of cosines, just like there was the law of sines. I like the first one much better, and then I always figure out the last two. So if you memorize the first two, just relabel them and figure out the last two. Right? Now, how can you remember this one? What's a real easy way on this one? What does that look like?
Pythagorean theorem.
Yeah, there you go. It's Pythagorean theorem. And so this actually, if angle C is a 90-degree angle, becomes the Pythagorean theorem. This is actually a generalization of the Pythagorean theorem to non-right triangles. If you put in a 90-degree angle, you derive the Pythagorean theorem as a special case, right? Because cosine of 90 degrees is 0, and you just get that. But it shows more generally when C is not a 90-degree angle, this is how the sides and angles are related. So, and what's more, it's easy to remember because it's C squared equals A squared plus B squared, the Pythagorean theorem, minus 2AB, so AB cosine C. So if you know your ABCs, you can figure this one out, right? So this Pythagorean theorem minus 2 AB cosine C. Right? Well, that's how I remember it anyway. I think it's a lot easier. These things need some sort of device to be able to figure them all out, right? So this is a longer rule, but it's not too hard to remember because of the Pythagorean theorem and the ABCs. All right. Now, we said before that this one is convenient. Even though it works for any triangle, it's only convenient if you can write an equation with all but one known, right? So this is convenient. We can write an equation with all but one letter known and then solve for the last letter that's left. This is convenient given side, 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 or side, angle, side in a triangle. Any other case, you don't have one of those, you'll have two unknowns in the equation, you won't be able to solve it right away. You have to write like two equations, two unknowns, to solve it too. That's a mess. It's easier to drop a perpendicular and use right triangle trig. So this is faster if you get those. And the idea is now we can cover all oblique triangles. What an oblique triangle is a non-right triangle, right? So we can cover any non-right triangle now quickly with either the law of sines or the law of cosines. If you have one of these, use the law of cosines. If you have anything else, use the law of sines. If you have a right triangle, you don't bother with this stuff because it's easier to right triangle trig. All right. So, let's see. Have- Yeah, let's do this example first. This is one of my favorite examples, actually. You've all seen a 3, 4, 5 right triangle before, right? What if somebody gave you a 3, 4, 6 triangle? No longer a right triangle because a squared plus b squared is equal to c squared. It doesn't satisfy the Pythagorean theorem. Can't be a right triangle, right? So as I said, solve this triangle. So use the law of sines or the law of cosines. Yeah, it's side, 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 so it's law of cosines. Right? So use law of sines, I won't get all but one number known, and I won't be able to solve it with just one equation. So I use the law of cosines, then I will be able to. Right? So I just want to find all these angles. Now, this you can label these angles any way you like. I like to put A opposite the smallest number, and B opposite the next smallest, C opposite the greatest. Remember the rule on these things that you can check, but the largest angle always goes opposite the largest side, and second largest, next to second, third one to third. It reminds me of the right triangles where you always make C the hypotenuse the largest, but you don't have to do that here. You can do it any way you want. I just like to do it that way. So the law of cosines applies, and I'll use the first one because it's easiest for me to remember. And I'll say C squared equals A squared plus B squared minus 2AB cosine C, right? Becomes, let's see, C is the largest side I made there. 6 squared equals 3 squared plus 4 squared minus twice 3 times 4 times cosine C. And you notice I know everything except for angle C in this equation, so I can solve for it, right? What's more, the law of cosines is nice because it doesn't have an ambiguity, right? And in the law of sines, you saw you got sine beta equals number, and it could be arc sine or it could be 180 minus the arc sine. Not here. This one always just comes out to be an arc cosine, so it's a little better like that. You don't have ambiguities. All right, so what I have to do is solve for cosine C. This is mostly algebra and what you do is you subtract these over and get 6 squared minus 3 squared minus 4 squared equivalently is equal to, let's see, 2 times 3 times 4 is 24, right? So it's equal to minus 24 cosine C. I just subtracted these two numbers over here and wrote 2 times 3 times 4. Now I divide by 24 and minus 24, and I've got cosine C equals 6 squared minus 3 squared minus 4 squared all over negative 20. Oh, wait a minute, I'm gonna get a negative number here. This is always something that throws you. How can I get cosine equal to negative? Actually, that's okay. You don't ever get the law of sines with a negative because the sine of an angle between 0 and 180 is always positive. But the cosine of an obtuse angle is negative. All this tells me is that I have an obtuse angle, right? So the cosine can be negative. Got an obtuse angle. So now, how do I solve that angle, I wonder? Easy, it's always the arc cosine. It's not the ambiguity. So just say cosine C equals that. C is the arc cosine. Done, right? Arc cosine of 6 squared minus 3 squared minus 4 squared all over minus 24. And I run that on my calculator. And I got, let's see. Hopefully something good. Inverse cosine of, and you need parentheses here again. Recall on your old calculators, if it doesn't use a long bar, then you need to enclose this in parentheses, or it will do the subtractions after it does this last division. So I'll take 4 squared divided by 24 and then subtract that from 3 squared and 6 squared. You get the wrong number. So make sure these are in parentheses or that you have a long bar here. Okay, arc cosine, I put my parentheses in. 36 minus 9 minus 16, doing the squares in my head. Close the parentheses, divided by negative 24. Let's see what I got. I got 117 degrees to the nearest degree. So there's one of the 3 angles, right? Here's what you need to do in the law of cosines. Oh boy, we're running out of time. Is you find one angle by the law of cosines, but this is kind of complicated and longer than the other angles. So you only use it once. You can use it again to find the other 2 angles. But what's easier than using the law of cosines is usually to use the law of sines. So that's one. I'll use the law of cosines for the first step. And then step 2, I'll use the law of sines because it's faster. And I'll say, once I have an angle, sine 117 degrees is to, that's angle C is to side C, 6 as sine of one of the other angles. Let's go for B, I guess. Doesn't matter. Is to side B, which was 4. And now you can solve for B. So you get 4 by some multiplying by 4. 4 sine 117 degrees over 6 is equal to sine B. And now we're getting down to an ambiguity, do we? Sine B equals a number? It looks like an ambiguity, but it's not. Actually, I know immediately B is the arc sine. It's kind of an important point. I hate to put it right at the end. I'll have to emphasize it again next time. B is the arc sine, not 180 minus. How do I know it's not 180 minus this time? This is the trick I worked ahead on. What you do is when you use the law of cosines, try to solve for the largest angle. I know the largest side goes opposite the largest angle, so I solve for the largest angle first. And now a triangle can have at most one obtuse angle, right? It can't have more than one angle that's more than 90 degrees, because 3 would add up to more than 180 degrees, right? So the angles A and B that are left are acute angles. So it can't be 180 minus arc sine. That would be an obtuse angle. It's only arc sine since B isn't the largest angle. It can't be obtuse. Have at most one obtuse angle. So I just compute the arc sine. I don't have an ambiguity when using the law of sines. Let's see what it comes out to be real quick, and then we gotta get inverse sine. Inverse sine. I get 36 degrees. And then the last one is easy. So you just subtract. You say, I've got B and C. We'll say angle A is 180 minus the ones we found. 117. Where'd it go? 117 and 36. Those are 153. So I got apparently 27 degrees. All right. And you can do the sanity checking and make sure the largest angle is opposite the largest side and second largest opposite second largest. Looks like it came out that way. So there's the 3 angles we're missing. Well, find the homework, and I think you'll find this one is a little easier. And I'll do the side angle so in case next time.
So after we get like one of them, we can use the law of sines? Or
Yeah.
can we use the law of
The
cosines?
law of sines and law of cosines apply to any triangle, so you can apply them any time. But what happens is if you have side, or side angle side, the law of sines will give you an equation with 2 unknowns and you won't be able to do anything. So use the law of cosines for one of these 2 cases, then you get one angle, one more measure. And once you have that, you use either one. But the law of sines is shorter.
Yeah.
All right, have a good minute.
Me too. Is there any way you can tell me what I